Okay, now when we actually solve them, we want to put this together. So how do we actually solve for this governing equation? How do we do that? How do we do that? Well, the way to do this is actually very simple. Is first of all, there are different approaches depending on the type of problems. Suppose we consider the general condition, which means that you have both mass, stiffness, damping, all three of them. We consider damped systems. And to find the solution, what we will do is usually to multiply everything, the entire governing equation, by the inverse of your mass matrix. So if you subject this term, the inverse of the mass matrix, multiply everything by this. To the whole thing. So here, the first one is still mass matrix times acceleration vector. And the second one is still damping matrix times velocity vector. The third term is still stiffness matrix times displacement vector. This will equal to, on the right hand side of the equation, the inverse of mass matrix times your forcing vector, which is like this. Now, when you subject the inverse of the mass matrix to individual terms, from linear algebra, not matrix analysis, from linear algebra, the product of an inverse of a matrix to itself is what we call identity matrix. That means everything is zero, and the product between an identity matrix with any vector or any matrix is just going to be the matrix or the vector itself. So the product of these two will just give you an I, n by I, and this I multiplied by the acceleration vector will become just the acceleration vector. So this is just like what? Just like when we deal with scalars. Any number multiplied by the inverse of itself will just become unity. So here, this will lead to only acceleration vector for the first term. Even though that my explanation may appear a little bit lengthy, but the effect of an inverse of a matrix multiplied by itself is nothing different from a set scalar multiplied by the inverse by its inverse. So the result is just going to be 1. So you have this result to become inverse of the mass times the damping times velocity vector plus the inverse of mass matrix times the stiffness matrix times displacement. This equals to this. Now, one thing you will notice is the second term really depends on what we call the modal dependencies of this damping matrix, which is why next week we will focus on formulation of this damping matrix, because this operation will lead to several possible results. In some cases, the second term can be highly simplified. But today we will just live with this current form. And the third term, you must be familiar with this one here. And what we did before is, if I divide everything from the governing equation of a single degree of freedom system by mass itself, you know, mass will cancel out, the second term will become C over M, the third term will be K over M, right? And K over M, as we know, is what? Is the square of undamped natural frequency, correct? You remember this, right? What is K over M? K over M is just omega n squared. right? What about this one? The inverse.
Hey, Professor, can you hear me?
Yes.
Could you repeat what you said that you just wrote up top? Because for some reason my video is really blurry. So I'm writing as you're saying it. So could you repeat what you just wrote that you just boxed at the top?
Can you see here?
Please.
Sure.
I can see that you wrote something, but I don't know what it is. So I'm just trying to write really quickly as you're saying it.
Okay.
I don't know if anybody else is doing the same.
All right. No. Let me know, because we are all trying this, right? Is that because of the color? How about I use what if I use blue? It's gonna be better. K over M equals.
Yeah, I think the red is just making it really hard to see.
All right. No more red markers. How is that? How can you see it?
That's definitely better.
Better?
Yeah.
Is that K over M? Is that what you have?
Yes. K over M equals M squared. And why this? Of course, it's because we said that omega n is what?
Square root.
Square root K over M. So of course, this is just the same thing. You can either keep the square root on the right-hand side of this expression or subject both sides to square. And in other words, you can either say that omega n equals the square root of K over M, or you can say that omega n squared is K over M, right?
Yeah.
Mathematically, correct? Right?
Yeah.
Use this concept. Come back to look at this one. So what's this one here? This one is not. This one is not exactly K over M, but is the inverse of mass matrix times stiffness matrix. And keep in mind that it has to be carried out this way. Has to be carried out this way. So this is not exactly like a single degree of freedom, because in this case, you are only getting one term, which is omega n squared. But right here, if you multiply stiffness matrix by the inverse of mass matrix, so what are we gonna get? Are we gonna get a value, or are we gonna get a vector, or are we gonna get a matrix?
Matrix.
We're gonna get a matrix, right? For those of you who have taken linear algebra, that's what we call dimensional consistency. But a quick explanation here is you operate a matrix which has n by n. So each one of them will have to deal with one element in the stiffness matrix. So the outcome, of course, you're not going to sum up everything together. So there's no way you can get just a single value here. This operation will also lead you to a matrix. And as a result, this matrix has something to do as what we call modal frequencies. Now, the result is not that straightforward here unless you decompose them into what we call the modal factors here. So now if you live with this one at this point, and I'm going to come back to, so let me use the space here. I need every inch to explain this clearly to you. All right. Okay. All right, so this is what we have up to this point. All right. Right here, right? Correct? Now, so let's continue this part to here. What did we say that we can write this displacement? We said that in multi-degree of freedom system, dynamic displacement can be represented as the superposition of and product of mole-shaped vectors. And what we call generalized coordinates, right? So you would just treat this U as this, because U of x and t, one is for space, the other is for time, equals to the summation of I equals 1 to n bi times z t. One is space and the other is time, space time, like the one I gave you before. Now, I know this is only for dynamic displacement. What about for velocities? If I differentiate everything with respect to time, what do I get? I differentiate a displacement, dynamic displacement, with respect to time, I will get dynamic velocity vector, right? Is that correct? Right? You differentiate dynamic displacement vector with respect to time, you will get the dynamic, well, of course, everything is dynamic here. You will get a velocity vector. Correct?
Yeah.
I'm sorry?
Yeah.
Okay. Now, look at this. The time dependency is solely on generalized coordinates and nothing else. The time dependency is only on the generalized coordinates. Therefore, this time differentiation will only be subjected to generalized coordinates, correct? Because phi I is not time dependent, it's only space dependent, correct? Right?
Yes.
Right.
Therefore, we can then write the expression for velocity vectors as this. It's still the summation from I equals 1 to n, depending, n is the degree of freedom, times mode shape function, shape vector, phi of x is unchanged because it's not time dependent. It differentiates with respect to time, but this is a space dependent. It depends on x, so you will treat it like a constant, multiplied by the time derivative of generalized coordinate. So this differentiation will only be effective on generalized coordinates. Correct? Because of the assumption we made here. We said that displacement can be written as a summation of products between the shape vector and generalized coordinate. And one of them is space dependent, the other is time dependent. Therefore, this time differentiation will only apply on z, which is the generalized coordinate. If this can be established, and then the next one is much easier. Next, we differentiate again. Now you know that the result, not surprisingly, will be almost the same, except the second term. The generalized coordinates will be differentiated twice with respect to time, while the shape vector will remain untouched. So this will become z double dot of I as a function of time. Which means what? Which means, if you look at this time derivative only applies to generalized coordinate. Generalized coordinate. Shape vector remains unchanged. Is that clear?